Okay, in this unit we're looking at thermodynamics. Really, thermodynamics is just a study of conservation of energy. So let's review for energy. We know that energy is conserved. Thinking of a roller coaster, and let's look at the cards going up this hill. First, it starts off with a certain amount of kinetic energy, potential energy, and internal energy. And as it climbs this hill, it has to do work, and that work is going to be transformed as a transformation into a potential energy. But some of it's also needed to overcome friction, and so we can see that the potential energy is increased because work is energy is flown went into the system from work. But notice also the internal energy increased as well. That's really due to the thermal vibrations of the particles. At point C, the car has went down the hill, and now it's got more kinetic energy. It's less potential energy. But again, notice the internal energy is increased even more. That's because air resistance and even more friction along the rails. At point D, it's almost all kinetic energy, hardly any potential energy now. But again, notice the internal energy is increased. Again, more thermal energy, the vibrational energy of the particles that can't ever really be recovered. And then finally at the very end, at point E, it has potential energy, has some kinetic energy, and lots and lots of internal energy. So this section, we're going to be looking at that internal energy. We know that if there's any change in energy of a system, that's going to be from the sum of the transfers into or out of the system. Well, there's different ways you can transfer. You could transfer in terms of work. You could be transferring in terms of heating, that's Q. You could be transferring energy through radiating, that's R. And the way you could be changing the energy, you could be changing the internal energy of the system, the potential energy of the system, or the kinetic energy of the system. So let's use an example we might have seen last year in energy. Now this type of question right here will not be on the AP test, but I want you to kind of see the correlation to what we studied last year in thermo. Let's say we have a 500 kilogram drone airplane flying at 80 meters per second at an altitude of 2,500 meters, and it loses power and crashes. If the plane is made of aluminum, what will be the temperature change of the plane? Well, we know that the change in internal energy plus the change in gravitational energy plus the change in kinetic energy, if there is any changes, would have to be the result of any transfers into or out of the system. And that would be through heating, through working, or through radiating. In this situation, we're going to say there's no energy that's going into or out of the system through heating, working, or radiating. But there will be a loss of potential energy, mgh. There will be a loss of kinetic energy, 1/2 mv squared. Well, where does that energy go? Well, it must go into the internal energy of the aluminum particles. They're vibrating faster. So we can figure out the change in potential energy, change in kinetic energy, and that must be equal to change in internal energy. And we get 1.41 times 10 to the 7th joules. Now that kind of stuff actually would be possibly on the AP test. This next section, this next part of it won't be. Actually figuring out the temperature change of the aluminum. You'd have to use something that we know from chemistry, which is the change in temperature is given by the formula mc delta T, where m is the mass of the aluminum, c is the specific heat of aluminum, delta T is what we're trying to find. All these changes in temperature, by the way, in this unit will be with the absolute temperature scale, Kelvin. So we know the mass of the aluminum is, it's 500 kilograms. We know the specific heat of aluminum, and that's in the table, we can find that. So that means we can figure out the change in temperature. Solving it, we get 31.4 degrees Celsius. Okay, so that's kind of a tie-in from stuff we did last year until this year. It really kind of bridges the gap. Now let's consider a case where heating of a system gas can result in working being done. So a second ago we kind of saw how there's working, well actually there was a change in internal energy which resulted in a change in temperature. Well, can we have heating being done that would actually result in working, kind of reverse? Well, let's imagine maybe heating up some water in a Erlenmeyer flask, and on the flask we have a balloon attached, and it starts heating up the balloon. On top of the balloon we have this weight. Clearly, you can see the weight, increased in its height, so therefore work was done to it. So again, change in energy must be equal to the transfers into or out of the system. In this case, there's no radiating. There's no change in gravitational energy or kinetic energy of the system being the gas. If you're looking at the center of mass of the system, it does not change in height appreciably, and it's not changing in its speed translationally. It's not moving up, down, left, right, or anything like that. So the only thing that's going to be changing about it will be the internal energy. This is the first law of thermodynamics. Change in internal energy is equal to Q plus W. Very simple stuff we've seen before. We actually never really called it this before, but we've studied this already. The change in internal energy is equal to Q plus W, and the change of energy is equal to the sum of the transfers into or out of the system. Now we need to know some conventions here. One convention is if heat is added to the gas, or I should say if there's heating occurring here to the gas, Q will be positive. If energy is removed from from the gas through heating, then Q will be negative. If there's no energy transfer through heating, Q will be 0. If there's working done on the gas, so it's compressed, then W will be positive. If working is done to the environment, so the gas expands, then W will be negative. And if there's no transfer of energy through working, W will be 0. So let's try an example problem. 100 joules of heating is done to a gas system, and the system expends 40 joules of working on the environment. What is the change in internal energy of the gas? Okay, so start off with conservation of energy, better known as the first law of thermodynamics. And let's see, some stuff we know. 100 joules of heating is done to a gas. So heating is being put into the gas. So that 100 is going to be a positive. That goes in for Q. And it says 40 joules of working on the environment is done by the gas. So the system expends 40 joules of working on the environment. So that's going to be a negative 40. The gas is expanding. It's losing energy through working. And we need to figure out the change in internal energy system. So it's going to be 100 joules plus negative 40 joules. That would be 60 joules. Let's try another one. A total of 135 joules of working is done on a gaseous refrigerant as it undergoes compression. So notice working is done on the gas. So in this case, work is going to be positive. And another way I could tell it's being done on the gas is being compressed. So if I'm imagining this, I'm imagining that balloon, it's being compressed. There's a force inward, there's a displacement inward. That's positive work on the gas. If the internal energy of the gas increases by 114, so change in internal energy would be positive 114. We need to figure out what is the total amount of energy transferred through heating. So we have to figure out Q. And then finally, has energy been added to or removed from the refrigerant during heating? So I start off with conservation of energy. Change in internal energy equals Q plus W, better known as first law of thermodynamics. I plug in the positive 135 joules for the work, and I plug in a positive 114 joules for the change in internal energy. Solve for Q, and I get negative 21 joules. And since it's negative, that means it's been removed. So that answers both of those questions.